Good morning, good day. It's a great pleasure and the honor to present on Huawei workshop. And thank you, Valentin, for the introduction. And today my topic is conversational artificial intelligence. Actually, the term conversational AI emerged just maybe 3 or 4 years ago, and it seems like a rebranding of the well-known area in NLP, which was previously called dialogue systems. But on the other hand, today we have a greater demand as for NLP in general, and as well is more attention is paid to conversational, to dialogue systems and conversational AI. So why conversational AI today is so important that we have on almost all major conferences like NeurIPS or ICML, which are not tailored specifically for natural language processing, but and also on the EMNLP and ACL conferences, we see many workshops devoted to conversational AI. I think that it's clear from this picture that in just 10 years, we have seen emergence of new world of new means of communication, new world of textual communication between people. And this is how people interact with each other more and more time spent in textual channels. So companies are interested in producing systems to understand what users say to each other and what users say can say to the support system, for example. And this is important for businesses. On the other hand, we have a smart home, and to control these smart homes, we need either complex applications which you need to learn how to use them, or you can just use your voice to control your home, which is much more natural. And this is why smart speakers as a hubs for smart home controls are so popular right now. And certainly also conversational AI is one of the major parts of our understanding of what should be our ultimate universal AI assistant. Because this natural language communication in natural language and setting tasks in natural language is like the one of the most important features of such future AI assistant. This is why we have a great interest in conversational AI right now. So what is conversational AI? Usually, if we take a look at the traditional architecture of the modular dialogue system, we can see here that we have a user have some request. This request goes to the first part of our dialogue system, which is the natural language understanding part. And this natural language understanding part performs domain detection. Here it's movie, intent detection. Here it's request of movies, and entities detection, which is required to better understand user request. Then this information goes to the dialogue manager. Dialogue manager needs to update current dialogue state and then use some policy which has the full dialogue state with the full history of communication with the user that decide what should be done with this request. And here, dialogue manager says that we need to get information about location of the user, and this action goes to the natural language generation part, which use some generative models or templates to produce response in the form of natural language to our user. So this is the traditional way, and the majority of current dialogue systems are built in this with this architecture. And before the deep learning revolution, when we speak about this architecture and about this NLU part and this dialogue manager part, it was mainly implemented with rules And this caused large problems for implementing these systems, because it was empirically discovered that if you have more than 100 rules, it starts hard to maintain your systems, because you want to update your system, you want to add more rules, and then you have a conflicts between old rules and new rules, and you spend more money to sustain your system than to pay for for example, for user operators in your call center. And it also leads to the not very good user experience. But then we had this deep learning revolution, where we have great advances in natural language understanding and machine translation, with introduction of encoder-decoder with attention architectures. And it seems that we can apply this similar approach to our dialogue systems. So we have a natural language understanding part of our dialogue system, but we also have embedding of or encoder in our encoder-decoder architecture. We have dialogue state tracker, and we have some memory for tokens which were encoded by our encoder. We have a policy and natural generation, and we have attention and decoder, which use this memory as an input to decode output in our system. But it seems that still open domain dialogue is much harder than machine translation, and we are limited in application of this scheme right now. But still, let's take a look how we can apply neural networks to the problems of dialogue systems. Here you can see how we can implement these different parts of a modular dialogue system with recurrent neural networks. We can, for the task-oriented dialogue system, which is required to solve a specific, very narrow task. Here, for example, it's restaurant booking. So we have intent network, which is devoted to intent recognition. We have some belief tracker, which is entity detection part of our system. Then we have a policy network, which decides an action. We also have at the backend, we have some database and database operator, which allows us to query database to find here it's names of the restaurants, which are filtered with our current understanding, with our current dialogue state. And then we have a decoder generation network, which generates output of the user. And this is early application of neural networks to the task-oriented dialogue. And if we look at the performance of the system and compare it with a traditional modular way rule-based system, we can see that subjective success of solving task when we ask users how they feel about solving the task with these two different systems, we can see here that neural system has a bit larger subjective success, but it's not very different from the modular one. But on the other hand, it can solve the problem of the user in a lower number of turns. Here it's just 4 turns and 4.5 turns in modular system, which is actually pretty good for the user, because you spend less time for booking restaurant in this case, in the case of neural-based system. But the major difference is revealed that then when we can look at the subjective feeling about the process of booking. So if we ask human evaluators about naturalness, comprehension, preference, and performance of the system, they give score which 2 times higher in the case of neural architecture than modular. So we see that using neural models in the natural language generation part improves quality of user quality of the system. Today, of course, we are not using RNN. We are using transformer models for this type of task-oriented dialogue. And here is an example of how we can apply transformer architecture for dialogue state tracking and response generation problem. So we can use a transformer block and feed in with two last utterances from the user, and then we encode all possible pairs of slot of domain and slot in our system, and then we decide how to update, train the system to update dialog state. And then, given the dialog state, we reuse already encoded slot output of slot tokens, special slot tokens, to generate slot values and responses for the user. And we can, like, current state of the art in the natural language processing and what Ivan described as multilingual system offers us unique possibilities to build task-oriented system even without specific training on natural language understanding. Here is an example how we can use squad-based model, the models which can find answer in the text for slot filling, for natural understanding problem. So imagine that we have system and we have no data to train it for our domain, for restaurant booking domain, but we still want to create MVP and we want to create working system. So what we can do then, if we have a model which is pre-trained on Wikipedia to find an answer in the text, what we can do, we can take our user input and use it as an input to our system. And on the other hand, we just need to describe in natural language the types of data we want to extract from the user input. And for a restaurant domain, we have some schema, and we need to understand the name of the restaurant, and we need to understand party size for a reservation, and date for the reservation, and time for the reservation. So what we want to do, we don't want to provide any labeled data, but we just need to describe what kind of data we want to extract from the user dialogue, and then use these natural language descriptions as queries to our model. So what we do, we have a user query to our system, and we ask the question, what is the name restaurant? What our user thinks is the name of the restaurant? And it can find, without any additional pre-training or additional training on the task, here the name of the restaurant. So I'd like to make reservation at Parisian. So the system is able to find restaurant. Then we certainly can, like, put here party size for a reservation, 2 people. Again, we need no data to have this kind of slot filling. And date for the reservation, 5th of March. Time for the reservation, 5:30. But as Ivan told before, we can use also multilingual models. So if we want to localize our system, but we want to use the same scheme for scheme of data or the same ontology for the different language, so we can have user from Russia which wants to reserve table in Russia, in Russian language, but we can use like the same natural language descriptions in English, and model trained in English squad, not in Russian, still able to find the name of the restaurant. And let's try party size. But here you see the mistake that the model is unable to find only на двоих and includes столик на двоих together with the restaurant name. And for the date of reservation, it is correct. And time for reservation is also correct. So you can see that with already pre-trained model, you can easily create a very powerful MVP for restaurant booking. But today, dialogue systems are much more complex, and they solve not only narrow task-oriented problems, but also combine them with a chit chat to engage user in further interaction with the system. And today there are two main branches, two main approaches how to create chit chat models. It's retrieval-based methods when you have a lot of predefined responses and you need your model to rank them conditioned on the current dialogue context. And on the other hand, it's generation-based models. And then you have also context as an input for your model, and then you have generated input token by token. And in the first case, it's much safer approach because you can filter only appropriate responses in your database. And here you are not very safe because a model can generate something inappropriate in your case. But on the other hand, you have much more adaptable model, which with much more diverse answers, and which can align answer much closer to the context than retrieval-based one. And what is happening here? And from the beginning of the year, there were three major chit-chat models published. The first one is a Google Miena, which is based on the specific transformer block, evolved transformer block, and it has 2.6 billion parameters and trained for 30 days on TPU report with 40 billion words. And you can see here that it's blue dots, it's different model sizes. And when we have a larger and larger model, it has like subjective quality closer and closer to human. And here are the examples of rule-based bots like Cleverbot and Mitsuku, and complex bots like Huawei. And you can see that Miena outperforms in terms of subjective subjective quality this system by human evaluation. But then after this paper was published, another one came out. It's from Facebook AI Research, which was called BlenderBot. You can see here that it has also 2.7 billion models and 9.4 billion models. And here it's much more powerful. And if authors compared it to Miena, and it shows that this is human preference. What continuation of the dialogue human will prefer from BlenderBot or from Miena. And you can see here that clearly for large models, human prefer BlenderBot to Miena with statistical significance. And they also compared different versions of the BlenderBot and Miena to human continuation. And you can see here for the large BlenderBot models, they are very close to the human. So it's hard for the human evaluator to distinguish between model and human, between responses produced by the model and human for the given conversational context. But certainly it's not the end, because then we had OpenAI GPT-3, and here you can see that when we take different model sizes, bigger and bigger models, the largest model, and we have a task, but here it's not the task of continuing dialogue, but the task of generating news articles. But anyway, you can see here that this model also produces text which is almost indistinguishable from the human-generated text. So, but still, there are problems in these types of generative models. When you continue dialogue with them, they lose context. They cannot differentiate some contradictions with their previous responses. So they lack like more or less common sense and inference in their responses, and they also lack goal-directedness. So they have no goal in their dialogue. And this makes it this type of dialogues a bit wild. But let's switch from the research to the production. So what models are currently used in industry? And today it's mostly hybrid system when you have multiple skills. Here is a diagram for Alimi Assist, when you have different services like intention classifier, intent detection component, assistant service, customer service, chatting service, and they are connected by some logic based on the rules. Another notable example is Huawei social bot, which is like the most popular social bot in the world, more than 600 million users worldwide, and it has a quite complex architecture where it has a lot of components like a general chat, domain chat, a lot of skills for task completion, deep engagement, content creation, image commenting, a specific part very important for social bots, if empathetic computing, to understand user, to use some social skills, and to reveal Huawei's personality, and of course this shared memory, global state tracker to understand what components should be used in the current dialogue term. And here is just a short, brief view how many different skills, conversational skills this agent has. It's personal, emotional skills, rational skills. I will not dive into details here. And after deployment of this bot in 2014, in 3 years, it reaches level average number of turns in the dialogue on the level of 23, which is comparable to the human dialogues. So it can comment photos with joke and provide sympathetic responses given some pictures. And as I've said, it uses different conversational skills during dialogues. And you can see here some exemplar dialogue, and it has a chat, question answering, chat, image search, recommendation, QA, and chat skills used in this particular dialogue. And it also has some prediction model which predicts sentiments of the user's utterances, and then use these predictions to control mood of the user. So if we have some negative emotions at the beginning of the conversation, the system tries to improve the mood for the user and tries to use responses which has a high probability to invoke responses from the user side with the positive emotions. And it's pretty nice to have a system which can cheer you. And so let me briefly conclude with the first part of my presentation. So currently in the field of conversational AI, it's very rapidly developing. We have deep learning solution, and mostly current solutions in the industry are rule-based, use classic ML, use deep neural networks. And we see emergence of multi-skill dialogue agents, and language models here helps a lot. Many datasets publish it, but still common sense is a challenge. But what is the next steps for the conversational AI? Certainly, you can see that personal assistants, they have more and more skills, means the third-party skills on this platform means that its companies, third parties create intelligence for these personal assistants, and it's very similar to what was envisioned by Marvin Minsky, one of the fathers of artificial intelligence, in his theory Society of Mind, when he hypothesized that our mind is a society of cognitive agents evolved over the evolution. And these cognitive agents cooperate to solve our task. And it's very similar to this multi-skill conversational agent like Amazon Alexa or Yandex Alisa or Google Assistant. And this is where we are trying to make a dent, where we're trying to contribute to this field in our Deep Pavlov project. We are creating open source framework like a dialogue operating system, in some sense another DOS compared to the Microsoft DOS operating system. And our framework is called Deep Pavlov to commemorate Russian neurophysiologist Ivan Pavlov. And what we want to solve, if you look at the current AI assistant lifecycle, what you are usually doing, you are starting from MVP with NLU and dialog manager. And when you deploy it, you add more and more features and more scripts to a dialog manager, and it starts unmanageable. So you cannot grow it anymore. And we want to create a much more controllable situation when you encapsulate your task-oriented, narrow dialogue skills in some conversational skills, and then you use orchestration. And you use DP agent to orchestrate these skills, and you have a nice structure where you split your complexity of your control between orchestration and domain skills. And to implement this, we have a framework which consists of our Deep Pavlov library. It's a library of NLP pipelines. And we also have a Deep Pavlov agent, which allows you to orchestrate skills created with these NLP components from the Deep Pavlov library. So for every different conversational skills, you can use different NLP pipelines. And we have Deep Pavlov Dream, which is a repository of different conversational skills, so you can use them to build some MVPs of your complex agents. So I will not give you complex details about Deep Pavlov library. Here is the components and skills currently in our library. And we use our Deep Pavlov agent framework and Deep Pavlov library to build Dream social bot architecture, which was our competition solution for Alexa Price social bot. And you can see here that it has a pipeline with annotators run as a microservices, skill selector, which runs conversational skills, and every skill produces its response candidates. And then these response candidates are selected by response selectors. And all this has a shared memory. And all this is open source solution you can use in your solutions. Here is how it is deployed on your infrastructure or in cloud infrastructure. So pipelines are run as annotators and microservices in your cloud, as well as skill, and then you use agent to orchestrate all these components to create your AI assistant. So if you have a look, concluding, if you have a look at the conversational AI stack right now, then you see that Deep Pavlov library covers 3 levels of the stack. It's NLP pipelines, NLP frameworks, it's conversational skills, and multi-skill orchestration. And this year, again, we are participating in Alexa Prize social challenge, and we will develop our framework further and also want to push boundaries of conversational AI with our technology. So thank you for your attention. Thank you.